Welcome to the deep dive. Today, we're tackling one of those science concepts that feels like it should be simple.
Yeah, heat and temperature. Sounds straightforward.
Right. But here's a question for you. Really think about this. Can two objects have the exact same temperature reading?
Hmm.
Meaning they feel, equally warm or cold, but hold completely different amounts of heat energy inside them.
It seems like it shouldn't work that way, does it? Like the thermometer tells the whole story.
Exactly. It feels like a paradox.
But figuring out this difference between heat and temperature, it's actually super important. It explains so much.
Like why your soup gets cold, or even, big picture, how weather works across the globe.
Absolutely. Energy distribution
So that's our mission for this deep dive. We're going to really focus on that key distinction. Heat as the total stuff, the total energy.
versus temperature, which is more like an average measure.
Yeah, the average motion.
But
We'll use some fun examples you might have heard, boiling cups, icebergs, that sort of thing,
the classics.
to help you really get your head around it quickly. So let's start with the basics. Heat. What actually is heat?
Okay, so in physics, when we say heat, we mean energy that's moving. It's energy in transit.
Moving.
Yeah, being transferred. And the key thing, the absolute rule, is that it always flows naturally from something with more energy.
The hotter thing.
Right, the hotter object to the one with less energy, the cooler one. It won't go the other way on its own.
That direction is key then. Hot to cold, always.
Always.
And since it's energy we're talking about, we measure it in joules, right? The standard unit.
Yep, joules or J. So
Yeah.
if you measure heat, you're measuring the total energy that's moved or could potentially move.
Okay, joules for heat, the total energy transfer. Now, temperature. How is that different?
Temperature is completely different, really.
Mm-hmm.
It's not about the total energy. It's the measure of the average kinetic energy of the particles inside something.
Kinetic energy, that's movement energy.
Exactly. How much the atoms or molecules are moving, vibrating, jostling around. Temperature tells you the average intensity of that motion.
So, like, how fast the tiny bits inside are wiggling, on average.
That's a great way to put it. Faster wiggles mean higher temperature. Slower wiggles, lower temperature.
And, okay, this is interesting. You're saying temperature doesn't depend on how much stuff there is.
Not at all. That's the crucial part. You could have one tiny water droplet or an entire ocean. The temperature reading just reports that average particle motion within it. Size doesn't matter for the temperature reading itself.
We usually see that average motion measured in Celsius or Fahrenheit on our thermometers.
Those are the common ones, yeah.
Yeah.
But you often see scientists using a different scale, Kelvin.
Ah, Kelvin, the absolute scale.
Right. And that actually brings up a neat question for you to ponder as we go along. Why do scientists prefer Kelvin? Why does it start at 0?
Absolute zero.
Think about what that 0 point might mean for those wiggling particles we just talked about. Keep that in the back of your mind. We'll circle back.
Okay, we'll do. So let's nail down this core difference now. This is the real aha moment, isn't it?
It really is.
Temperature is just the average speed, the average wiggle. But heat is the total energy, everything combined.
Yeah, think of it like traffic.
Mhm.
Temperature is maybe the average speed of the cars on the highway,
Okay.
but the heat is like the total energy of all the cars. That depends on two things, right?
How fast they're going.
Which is like temperature.
And how many cars there are.
Exactly. The mass, the amount of stuff.
So heat, average speed, temperature, multiplied by the number of particles, mass.
Pretty much sums it up. And that's why we get those examples that sound weird at first.
Like the classic one, the boiling cup versus the bathtub.
Perfect example.
Okay, so imagine a small cup, maybe 200 milliliters of water that's just boiled. It's at 100 degrees Celsius, steaming hot.
Right, very high temperature. Particles moving super fast on average.
Now picture a huge bathtub full of water. It's just warm, maybe 40 degrees Celsius.
Much cooler temperature. Particles are moving slower on average than in the cup.
So the cup has the higher temperature, no question.
Definitely. 100 C versus 40 C.
But which one has more heat energy?
Now you have to factor in the amount. That bathtub holds, what, maybe 100 liters?
Yeah.
Maybe 500 times more water than the cup?
Easily, yeah.
So even though the average energy per particle temperature is lower in the tub, there's vastly, vastly more particles.
So the total energy, all those slightly slower wiggles added up, is way more.
Way more. The sheer volume, the mass, totally outweighs the lower temperature. The tub contains much more total heat energy in joules.
Wow, okay. High wiggle speed in the cup, but just an enormous number of wiggles, even slower ones, in the tub. Tub wins on total energy.
You got it. That's the core idea.
Let's try making it a bit more interactive. Imagine we have 3 glasses of water, Keep track of the temperature and the amount.
Okay, I'm picturing them.
Glass A, it's got cold water, 0 degrees C, and it's 200 milliliters.
Okay, cold, 200 mil.
Glass B, hot water this time, 50 degrees C, but the same amount, 200 milliliters.
Right, hot, same 200 mil.
And finally, glass C. This one's just warm, say 30 degrees C, but
Yeah.
it's a big one. It's a full liter, 1,000 milliliters.
Okay. So same temp range, roughly as the tub example, but much larger volume than A and B.
Exactly. So first question, nice and easy. Which glass has the highest temperature?
That's clearly glass B, right?
Mhm.
50 degrees C. Its particles have the highest average speed.
Perfect. Now, the trickier one. Which glass contains the most total heat energy?
Okay, thinking about our rule, energy depends on average speed and the amount of stuff.
Mm-hmm.
Glass C is only 30 degrees, which is lower than B, but it has 5 times more water than A or B.
Yeah, 1,000 milliliters versus 200.
So even with a moderate temperature, that huge mass means glass C has the most total heat energy overall.
That really makes it click. You need either high temp or lots of mass or both to get lots of heat energy. It's that multiplication thing.
Exactly right. And this explains other things we run into, like the metal spoon in hot soup.
Oh, yeah. I've always wondered about that.
So you put a metal spoon in soup that's, say, 70 degrees Celsius. You leave it for a bit.
Okay.
After a few minutes, the spoon and the soup nearby are at the same temperature, thermodynamically speaking. Both are 70 C.
Wait, really? Same exact temperature?
Mm-hmm. They've reached equilibrium.
Then why, when I go to grab the spoon handle, does it feel so much hotter than just dipping my finger in the soup? It feels like it burns me instantly.
Great question. It's not about the temperature itself at that point. It's about how fast the heat, energy, transfers to your hand.
Oh.
Metal is an excellent conductor of heat. When you touch it, that 70-degree energy transfers very quickly, very efficiently into your skin.
Like a sudden rush of energy.
Exactly. It makes the temperature of your skin surface shoot up rapidly. The soup, mostly water, is a much poorer conductor.
So the energy moves slower from the soup.
Much slower. It still transfers heat, it's still 70 degrees, but it doesn't deliver that energy punch nearly as fast as the metal does. So the sensation is less intense initially.
That makes total sense. It's the speed of the transfer, the conduction.
Precisely. And since you brought up conduction, that's a perfect lead-in. Heat doesn't just sit there, it moves. And it moves in 3 main ways.
Right, the 3 methods of heat transfer. Conduction.
Which we just discussed with the spoon. That's heat moving through direct contact, particles bumping into their neighbors.
Like a domino effect of wiggles through a solid.
Good analogy.
Yeah.
Yeah, it works best in solids where particles are tightly packed. Touching a hot pan handle, that's conduction.
Okay, so conduction needs touch. What's next?
Convection. This one is mainly for fluids, so liquids and gases.
How does that work?
When you heat a fluid, like water in a pot or air in a room, the part that gets heated expands a bit and becomes less dense.
Lighter, sort of.
Yeah, effectively
know.
lighter. So it rises, and the cooler, denser fluid sinks down to take its place, gets heated, and then it rises too.
Ah, so you get this circulation, a current.
Exactly. A convection current. It carries the heat throughout the fluid. Boiling water is a classic example. You see it churning. Or warm air rising near a heater.
Okay, conduction by touch, convection by flow. What's the third one?
Radiation. This one's a bit different because it doesn't need any matter, any medium to travel through.
No touching, no flowing. How does it move then?
It travels as electromagnetic waves, like light waves or radio waves, but these are infrared waves, carrying thermal energy.
So energy just beams across space.
Pretty much.
Yeah.
The heat source emits these waves, they travel outwards, and when they hit an object, the object absorbs the energy, and its temperature goes up.
The biggest example has to be the sun, right?
Absolutely. The sun warming the Earth across millions of kilometers of empty space. It's pure radiation. Or feeling the heat from a campfire even when you're not directly in the smoke or touching it.
Okay, that leads perfectly into that little challenge question. We have conduction needs touch, convection needs fluid, and radiation needs nothing. Which one of those 3 is the only way heat can effectively travel through the vacuum of outer space?
Well, space is pretty much empty, right? No particles packed together for conduction.
Nope.
And no real fluid to circulate for convection.
Definitely not.
So it has to be.
Radiation, the electromagnetic waves.
You got it. That's how the sun's energy reaches us. Even though the space between is incredibly cold, the radiant energy travels right through.
Okay, let's bring this all home now. Let's connect everything back to that first paradox we started with.
iceberg.
Yeah, the giant iceberg versus the tiny cup of boiling water. It seemed impossible, but now.
Now it should make sense. You have this enormous iceberg, maybe sitting right at 0 degrees Celsius, freezing point.
Particles barely moving, just a little slow vibration.
Right. And you compare it to that small cup of water at 100 degrees C, particles going crazy, high average energy.
Higher temperature in the cup, for sure.
But the total heat energy, you have to consider the sheer, unbelievable number of water molecules in that massive iceberg.
Trillions upon trillions.
Exactly. Even though each particle has very little energy, low temperature, when you multiply that tiny energy by the enormous number of particles,
The total energy, the total joules, ends up being much, much greater than the total energy in the small cup, despite its high temperature.
mass wins again. Scale matters hugely when you're talking about total heat content.
And understanding that isn't just a fun puzzle, is it? You mentioned climate earlier.
Right. Think about Earth's oceans. They contain an immense amount of heat energy because of their huge mass, even though their temperature changes are relatively small compared to land. That massive heat reservoir helps stabilize our planet's climate.
So this distinction is actually critical for understanding big environmental systems.
Absolutely. And just for avoiding confusion in everyday life, too.
Okay, what a deep dive. Let's quickly recap the main point then.
The big takeaway. Temperature tells you about the average speed or kinetic energy of the particles, how intense the wiggle is.
Average speed. Got it.
Heat, on the other hand, is about the total energy contained within the substance. It depends on both that average speed and how much stuff, how much mass there is.
Average speed times mass gives you the total energy picture.
Keep that comparison average versus total clear in your mind, and you'll have mastered this, whether you're thinking about physics problems or just why your coffee cools down.
Perfect. And for one final thought, let's revisit that question about the Kelvin scale we parked earlier.
Ah, yes, absolute zero.
We said scientists like Kelvin because it's an absolute scale starting at 0. Temperature measures average kinetic energy.
So, why does Kelvin start at 0? What does 0 Kelvin physically mean for those particles?
Think about what happens if you keep cooling something down, reducing that average kinetic energy more and more. What's the ultimate limit?
What happens to the wiggles if you reach 0 energy? Something to think about.
It connects right back to everything we've discussed. Keep pondering that.
Until next time, keep noticing the energy moving all around you.
And keep diving deep.